Hello everyone, and welcome to today's exciting event. For the first time, we are streaming a live full-day webinar from the campus of the University of Illinois at Urbana-Champaign on emerging topics in geosynthetics. We have a fantastic lineup of speakers who are renowned experts in the industry, all presenting live from campus today. I'm Andy Durham, your host for today's event. I currently serve on both the Executive Council of the Geosynthetics Materials Association and on the Board of Directors for the Fabricated Geomembrane Institute. I'm also a senior geosynthetics engineer at Owens Corning. Before we get started today, I'd like to give you a little bit more information on the organizations facilitating this event. The Geosynthetics Materials Association is an industry organization focused on providing engineering support, business development opportunities, educational programming, government relations expertise, and industry recognition. The GMA influences specifications and lobbies on behalf of member companies and targets key U.S. states to expand the geosynthetics market. GMA also provides a network to exchange information, solve common problems, and develop mutually beneficial relationships. The GMA is comprised of 80 companies throughout the world, offering its members the opportunity to be informed, get recognized, and stay connected. The Fabricated Geomembrane Institute is an industry organization dedicated to advancing the use of fabricated geomembranes through education, research, and technology transfer. Factory fabrication of geomembranes reduces field welding, reduces installation time and costs, allows modular construction, and provides consistent seam and liner quality. FGI is comprised of over 40 member companies striving to provide the latest and most relevant information on the design, construction, and performance of fabricated geomembranes. There's some great opportunities to get more involved with both the FGI and GMA over the upcoming months. The Geo Dallas Conference is being offered by the GMA on October 16th and 17th of this year as part of the overall IFAI Expo. This conference will be an intense two-day educational event with several exhibiting companies. On October 24th, the FGI will continue their popular one-day short course series in Saginaw, Michigan in conjunction with member company Plastatech. There will be a manufacturing facility tour after the short course at Plastatech's facility. On November 13th and 14th, the GMA will host their twice-a-year lobby days in Washington, D.C., where member companies will visit dozens of legislators on Capitol Hill to promote the value of geosynthetics in the construction of our nation's infrastructure. And in February 2019, the biannual Geosynthetics Conference will be held in Houston, Texas, and will again be one of the largest geosynthetics gatherings in the world. So we're about to begin our webinar, and I want to go over a few items so that you know how to participate in today's event. You will have the opportunity to submit text questions to today's presenter by typing your questions into the questions box of the control panel. You may send in your questions at any time during the presentation. We will collect these and address them during the Q&A session at the end of today's presentation. The recording of this webinar and the PowerPoint will be made available after today's presentations on both the FGI and the GMA websites. And now I'd like to introduce our first speaker, Dr. Kerry Rowe. Professor R. Kerry Rowe is a distinguished professor of civil engineering at Queen's University in Kingston, Ontario. Professor Rowe is one of the pioneers of geosynthetics, with particular emphasis on the effectiveness of geomembranes and geosynthetic clay liners for containment applications. Dr. Rowe's research has also included tunneling in soft ground and reinforcement of embankments and retaining walls. He has developed new computational modeling and experimental techniques. His experimental work ranges from small-scale laboratory tests on system components to mesocosms, where a full-scale system is examined under controlled conditions, in some cases for more than a decade, and full-scale field monitoring from the Arctic to the Antarctic. Let's please welcome Dr. Rowe.
Oh, thank you very much, ladies and gentlemen. It's my great pleasure to spend the next 55 minutes talking about the service life of polyethylene geomembranes. The question we're going to be addressing is, how long will a geomembrane last? And that depends on many factors. First and foremost, of course, it depends on the geomembrane itself, the resin, the additives, and the thickness. But it's also going to depend on other factors like seams, wrinkles, its exposure conditions to the sun, what it's resting on, a GCL or geosynthetic clay liner or compacted clay liner, a cover soil, sand or gravel. Is there a protection layer and what are its characteristics? What is the fluid being contained? And what is the temperature? We know that liners with geomembranes can give very low leakage. The question is, for how long? So let's begin with the first of those items, and that is the geomembrane itself. And the first aspect of that affects service life is the polymer. And we're going to be talking about LLDPE, or linear low density polyethylene, but in particular about HDPE, or high density polyethylene, which these days typically has a medium density resin. Then there are some very important additives. They include carbon black for UV and antioxidants and stabilizers for a variety of reasons we'll get to. There are a number of index tests that characterize the important properties affecting the long-term performance of the geomembrane. And the first of these are two tests that give us an index to the antioxidants and the stabilizers in the geomembrane. The first of them is called the standard OIT test, and the second is the high pressure OIT test. And if we look at a common document that people use in the industry to specify geomembranes, it says that an acceptable geomembrane will have a standard OIT greater than 100 minutes with 55% retained at 85 degrees after 90 days in air aging, or 400 minutes initially with 80% retained after 90 days in air at 85 degrees, and 50% retained with UV exposure after 1600 hours. Well, let's talk a little bit about how we get those OIT numbers. It's done with a device called a differential scanning calorimeter, or DSC. And the details differ slightly depending on whether we're looking at standard or HPOIT, but in both cases we're melting the plastic in a nitrogen environment at a changing temperature that comes up to an isothermal temperature. And in the case of the standard OIT, we then introduce oxygen at a pressure of 35 kPa, and a test is conducted at 200 degrees Celsius. In the HPOIT test, it's 3,500 kPa pressure and 150 degrees. But in both cases, we're monitoring how long it takes from when the oxygen's introduced until we see an exothermic reaction due to the oxygen oxidizing the polymer and the beginning of oxidative degradation. And so it is an index which picks up some of the antioxidants and stabilizers in the geomembrane, with two tests so that we have a broader picture of what is there. So we need to specify something, and this is the typical way it's specified. And what we're going to look at in this talk is how these parameters affect the service life. And in particular, although only 400 minutes of HPOIT is required if you're relying on that option, there are now geomembranes with more than 10 times that amount. The high values of HPOIT are typically attributed to low or high molecular weight hindered amine light stabilizers, HAS or HALs. And we're going to look at what effect they may or may not have on long-term performance. The other very important characteristic is the stress crack resistance, and that's related to the resin. And GRI GM13 currently requires 500 hours. Over the years, it's gone from 200 to 300 to now 500. So here are 5 different geomembranes from 3 different manufacturers. And all of these meet the GRI GM13 specifications. But you can see there's quite a difference in the standard OIT, the HP OIT, and in the stress crack resistance. So the question you might well ask yourself, will these all last as long as each other? Well, we're going to try and address how those properties affect the geomembrane, but first, how do we consider the life of a geomembrane evolves? And here is a typical representation taken from Schwann and Kerner in 1998 with some modifications. And it shows some property of interest and how it changes with time. And we typically split the life of a geomembrane into 3 stages. Stage 1 is when those antioxidants I've just been talking about are depleting. And we say the geomembranes reach the end of stage 1 when the antioxidants depleted. And here we're seeing a geomembrane depleting to a very low residual value. Then there's an induction period. This is when the free radicals that ultimately will affect the surface life of the geomembrane are building up, but they're not sufficient to change measurably the physical properties of the geomembrane. The analogy I would give is to the development of a cancer cell. 1 cell becomes 2 cells, 2 becomes 4, but it's asymptomatic for a period of time. And that's the stage the geomembrane is in stage 2. But eventually with cancer, it becomes symptomatic. And the same is true for the geomembrane. Its symptom is a change in physical properties due to oxidative thermal degradation. And so a property of interest, it could be break elongation in a tensile test, it could be stress crack resistance, begins to decrease. And we typically say we've reached nominal failure when it drops to either 50% of its initial value or 50% of the specified value. Now that is going to be related to the service life, but it is not the service life. It is an index to the service life. The service life is when the geomembrane no longer performs its primary function as an advective barrier. If we look at this photograph of Ian Peggs, I think we can probably all agree this geomembrane's reached the end of its service life. Now that's a fairly obvious example, but the same thing can happen to buried geomembranes. And here is a geomembrane that was placed and loaded with no holes, no punctures, and yet after a period of time, as you see it here, it has 61 holes, which are stress crack ruptures, in a 0.6 metre diameter specimen. Now we typically design with maybe 5 to 10 holes per hectare. This is the equivalent of 2.2 million holes per hectare. I think we could probably agree it has also reached the end of its service life. Now that is a simple model. In fact, when we have HPIT being a significant player, as well as the standard OIT, it becomes a bit more complicated because we now have 2 OITs that can deplete. We have the standard OIT, which can deplete typically to a low residual value, and we have HPOIT, which often depletes to a relatively high residual value. And so the question is, how long is stage 1? One answer would be, it's to the last one reaches its residual. But is that in fact valid? Well, we're going to explore those questions, but let's first see how the antioxidants, as measured by an OIT test, change as a function of time. And here we're plotting the OIT, which started at a relatively high value, and it's been aged at 70 degrees Celsius, and you see it depletes with time. And we can fit a first-order equation to that, and it has two parameters, the initial OIT value and a rate of decrease S. Now, that equation can be replotted by taking the logarithm of both sides, and it becomes a linear equation. And so if we plot the logarithm of the OIT versus time, and we plot our data and put a best fit line through it, the slope of that line is the rate of antioxidant depletion. And we can quantify this for any geomembrane in any particular solution at any particular temperature. This was at 70 degrees. Let's take the same geomembrane and repeat the experiment. The only thing we change is temperature. And you can see we get very rapid depletion at 95 and also very rapid at 85. Somewhat slower at 70, a lot slower at 55, very much slower at 40, and virtually nothing happened in over 4 years at 25, which shows you that temperature is going to be a very important variable as we talk about how long a geomembrane will last. Now, what do we do with that data? Well, we often are not interested in the specific temperature the test was performed. We're interested in some other temperature. So how can we get it? What we do is we take the data, we plot the logarithm of the rate of change versus 1 over temperature in degrees Kelvin. And that then gives us a straight line. It means it fits an Arrhenius relationship, which is ubiquitous through chemistry and chemical engineering and applies, amongst other things, to geomembranes. So if we do the test at many different temperatures between 25 and 85 degrees, you can see they fit on a nice straight line. In fact, for this geomembrane, we can do tests up to 115 degrees, and they fit on the line. And this allows us to project what the rate would be at other temperatures which we didn't test. So the geomembrane itself is a very important part of the story, but it is only one part of the story. How long the geomembrane lasts not only depends on the geomembrane, it depends on what we do to it. We've seen that temperature is important. So too is exposure conditions. So if we leave it in the sun, that can affect how long the geomembrane is going to last. And one of the things in particular the sun will do, obviously, is heat it up. And we've seen that temperature is important. But also, it has UV radiation. And UV radiation has the ability to really accelerate the breakdown of the geomembrane. So to minimize that, protection is provided. The carbon black is the first level of protection. But then the antioxidants and stabilizers are put in, and they are going to provide additional protection. So if we want to assess how well it performs, there's two ways of doing it. One, which is very time-consuming but realistic, is to leave it out in the field and monitor it. Another is to use laboratory accelerated aging studies, and often a combination of the two provides real insight. I'm going to begin with a shorter-term field exposure of many geomembranes. I'm going to finish off with a longer-term field exposure and have some lab aging in between. But let's begin by looking at a number of geomembranes, some HDP, some LLDPE, left out in the sun at Queen's University for 2.5 years. So this is subjected to the nature as it comes, the weather conditions as they come. And a whole range of geomembranes of different thicknesses, some from exactly the same resin, the only variable was the thickness, others from different resins, were tested. And the first thing that becomes clear is that thickness matters. The thinner the geomembrane is, other things being equal, the faster the antioxidant will deplete and the quicker the geomembrane will degrade. But that is only one of the variables. Another very important one is the antioxidant and stabilization package, and that has a very significant effect. So if one compares LLDPE and HDPE, we can find that, in fact, the choice of the antioxidant stabilization package is more important than the resin in terms of how quickly those antioxidants disappear. Now let's go to the lab. And in 2008, Kerner et al. Published data at 70 degrees over 28,000 hours. And they looked at a 1 millimeter thick LLDPE and a 1.5 millimeter thick stabilized HDPE. And here is their data. And you can see both geomembranes perform very well up until close to the 28,000 hours. And then you can see them starting to decrease with the LLDPE dropping below 60% of the initial break elongation. And so we could look at this and say the LLDPE is degrading faster than the HDPE. But we have to remember, particularly in the context of just what I said, is that because of the resin? Or is it because of the particular antioxidant stabilizer package used? Or is it because of thickness? The other interesting thing in that work is that it showed that 1,000 hours lab time was approximately equal to 1 year exposure in Texas. So we can probably infer from this, if you take that relationship, that both geomembranes would in fact perform very well for about 28 years at least. Now let's get another study from Mills et al. 2009, where they aged two geomembranes, 0.75 millimeter thick and 1.5 millimeter thick, at 60 degrees for 30,000 hours. Now, in addition to a difference in thickness, they had very different antioxidant and stabilizer packages. And you can see that the HPOIT varied from 900 to over 4,400. And after 30,000 hours of aging, 69% of the OIT in the thinner geomembrane remained compared to 44% in the thicker. Now, as I said before, other things being equal, you would expect it to deplete faster in the thinner geomembrane. The reason it didn't is the difference in the antioxidant and stabilizer package. So just to summarize, some people have reported that the depletion of antioxidants is going to be faster in LLDPE than stabilized HDPE. And that may be true, but the point that I would make is you need to check, is it because of the resin, or is it because of differences in thickness, or is it because of differences in the antioxidant stabilizer package? If you want to make a conclusion about the resin, you really need the other things to be relatively consistent. And so it's difficult to generalize about which polymer is best unless you actually do that comparison. The other thing is that the loss of strength and elongation reported by Kerner et al. Suggests that whether one was using the 1 millimeter or the 1.5 millimeter LLDPE or HDPE, both were going to perform well exposed in Texas weather for at least 28 years. Now let's finish off this segment by going back to the field. And we're going to, for the first time, our Queen's University Environmental Liner Test Site, located about 50 kilometres north of Kingston in Ontario at latitude 44 degrees north, a little north of where we are at the moment, which is about 40 degrees north. And the geomembrane has been left out in the field to see what happens to it. We'll talk more about that in my second presentation. But for the moment, I'll note that this geomembrane had an initial standard OIT of about 170 minutes, HPOIT just shy of 800 minutes, and stress crack resistance of 500 hours. It's a pretty good geomembrane. After 6 years exposure for this south-facing liner system, the standard OIT had depleted to 55% of its initial value on the base. On the slope, it had dropped to 27% of its standard OIT it had initially. And the reason for that is, on a 3-to-1 slope facing south, you get a lot more direct exposure to the sun than on a flat base. Now the HPOAT was less affected because it was very well retained. In this case, there's over 80% still there after 6 years, field exposure on both the slope and the base. Now, at this point, it doesn't matter which of those you think is important, they're still there, so we are still in stage 1. And if we need additional evidence, there's no change in the tensile properties, there's no change in the melt index. But there is a change. The stress crack resistance started at 500 hours. After 6 years in the field, it's now at 190 hours. In the laboratory, that same geomembrane at room temperature without any exposure to the sun has dropped from 500 to 330 hours. I'm introducing this now to tell you that the oxidative thermal degradation we're going to talk about is not the only mechanism that can change geomembrane's properties. There can also be physical aging. Because when a geomembrane is manufactured, as it comes off the manufacturer's plant on a roll, it is not yet in a stable situation. With time, those molecules will rearrange themselves to a more stable state. And that's what we call physical aging, or I'm also going to refer to as morphological change. It can change some parameters by a little but significant amount, such as the yield property. It can change the crystallinity of the geomembrane. But in particular, for today's context, it can change the stress crack resistance. And in fact, it's the stress crack resistance after morphological change that will ultimately affect the long-term performance, not what it is when it comes off the roll. So these properties can all change due to morphology, nothing to do with oxidative degradation. But the rate is affected by temperature, which is why we saw faster depletion of the stress crack resistance in the field than in the laboratory. So let us now turn our attention to the fluid, because often a geomembrane is going to be there to contain a fluid, and that fluid is often a liquid. If we're lucky, it's nice clean water. If we're a little less lucky, it's distilled water. And if we're even less lucky, it is some sort of leachate or mining solution. So how about submerged and buried geomembrane liners? In all cases, extraction and oxidation are important, but it's especially important when we are submerged in a liquid. One way of assessing this is to take the geomembranes of interest, cut them into coupons, put them into bottles, surround them by the fluid of interest. It could be air, it could be any leachate that you're interested in, and put them in ovens and age them over time. And then periodically you take specimens and you test them, and you see how the properties are changing. Now the liquid used for the test you see in front of you has no colour. But you can see these jars have a colour. That is because of antioxidants that have depleted out of the geomembrane. So let us transition from the UV exposure to fluid exposure with a brine pond. Brine is a major issue in parts of the world where there is fracking for the collection of natural gases. And if we have a brine pond, the solution to be contained is very salty. It can be up to almost 10 times the concentration of seawater. And these brines not only have very high salt, but because of that, and because of stratification of density, the liner can get to very high temperatures because of energy captured by the brine. And they can be at temperatures of 40 to 95 degrees Celsius. So if we consider a brine pond, there are 3 domains of potential interest. The first, up near the top, is UV exposure. The second, located between the low and high waterline level, will be subjected to UV some of the time and brine immersion some of the time. And the third, below the low water level, is going to be subjected to immersion in brine all the time. So let us look at the latter. Let us take a geomembrane that has an initial OAT of 100 minutes, HPOAT of 260 minutes, no HALs, and we immerse it in a brine with a total dissolved solids at 200,000 grams per litre, so very salty. And we plot the normalized break elongation, that's the break elongation at any time divided by the initial value versus time over almost 4 years. And we've got results here for 4 different temperatures. At 40 degrees, there is very little change. But you can see at 65, 75, and 85, we have significant change. Not only that, at those 3 temperatures, even after only 4 months, we have a notable change. Now, the interesting thing about brine solution is they don't follow that nice model I started with. Because for 85 degrees, the HPOAT wasn't depleted until 38 months. But in terms of tensile break elongation at 85, it reached nominal failure in 21 months. And at 75 in 26 months, and at 65 in 34 months. So this is a very aggressive solution. Now you may well argue that that wasn't a good geomembrane. We could do a better one. We'll have a lot more OIT. We'll put in 160 minutes of standard OIT. We'll put in an HPOAT of 960 minutes. And this has HALs, so if you think HALs are going to solve the problem, let's test it. And it has a relatively similar stress crack resistance, a little higher at 800 hours. And here we're plotting 3 quantities versus time. The standard OIT is shown in blue, the HPOAT in green, and the stress crack resistance in white. And you'll see that the stress crack starts to degrade after 9 months, and it continues to degrade following a first order path. Indeed, it is degrading quite quickly compared to the depletion of the antioxidants, and the HPOAT doesn't deplete until 34 months. But the nominal failure in terms of stress crack is 25 months. And so we can see that in cases like this, it didn't really make a difference whether we had the high HALs or not. So let's take 4 geomembranes. We just looked at the first 2 in this table. We'll take 2 others. So we have 1 geomembrane with low HPOAT initially and no HALs. We have 3 with HPOAT from 600 to about 1100 minutes and all with HALs. And if we look at the time for HPOAT depletion, it's hard to see much of a correlation. The one with the lowest HPOAT was 30 months, the one with the highest was 32 months, the intermediate one was 34 months, and the one with no HALs and the lowest HPOAT was 38 months. But in fact, those are all irrelevant to its condition when immersed. The time for stages 1 and 2 in terms of stress crack for the 3 with the HPOAT are 9, 10, and 11 months. For the ones with the low HPOAT, it's 15 months. But in fact, what is critical is the initial stress crack resistance here. You can see that the first to fail, in terms of nominal failure, is MXC in 25 months. The second is MXA at 30. Followed by MYEW at 45, and after 4 years, MYE still hadn't failed. And if you ask why, just look at the top line. The initial stress crack resistance is why these last 2 are performing well. So just to summarize, MXA had a time to nominal failure of 30 months and better performance than MXC despite lower standard and HPOIT and similar stress crack. MYE had the best performance, but not because of its OIT package, rather because of its resin. And so, immersed in brine, the high HPOIT really didn't help. Now, that doesn't mean it may not be useful in a brine pond, because remember, I started by showing you it's going to be exposed to UV. It may be very useful for that aspect, but in terms of protecting it when it's immersed, it is not doing much. We are also just passing the 4-year mark on 5 other products that we're testing, which are actually all doing much better than these ones that we've published results for. So we've looked at brine, and it's a strange case, but it also is an important one. Let's now go to another important case, and that is landfills. And we're going to look at geomembranes in a municipal solid waste solution. And here we have 3 geomembranes, MYC, MXA, and MXB. They're all 1.5 millimeters thick. You can see there's a range in standard and HPOIT, and also quite a range by a factor of 3 in stress crack resistance. And we start by looking at the change in the standard OIT. And we see that both MXA and MXB are depleted in about 2.5 months. So the extra standard OIT, as we went from 100 to 160, didn't really make much of a difference, did it? The better performer in this case is MYC, which took 4 months. It also had the highest value. But what I'm trying to get to here, folks, is that it's not necessarily the high value that's important. It's the nature of the antioxidant that's important. Other things being equal, a good one and a bit more may help, but you also get to a point where putting even more in has no effect whatsoever. In terms of the HPOIT, this is what we get. Remember, there's quite a big difference in HPOIT in these 3. And we find that MYC, which has the highest value, has the fastest depletion, depleted in 4.4 months. MXA, with no HALs and the lowest initial value, took 7 months. And MXB took 10 months and it depleted to a high residual value. Now let's look at what ultimately really matters, the time to nominal failure in terms of stress crack. And here MYC, with the highest stress crack, had the longest time to nominal failure, even though it had rapid depletion of antioxidants. MXB, despite the slowest HPOIT depletion, was 19 months to nominal failure, and MXA, with the lowest OIT, took 14 months, despite a better stress crack than MXB. The point is, there's no clear correlation between initial values and how they're going to perform. In this case, again, we see that HPOIT was very little benefit for the immersed geomembrane. Again, I want to say that doesn't mean it's not important for other reasons, such as UV exposure. But when we immerse it, for at least these cases, it made no significant difference. So how long the geomembrane lasts is going to depend on the polymer. And if we just summarize the results we looked at for these 3 geomembranes at 85 degrees C, which is high, but as Tim Stark will be telling you this afternoon, they are landfills at these temperatures and even higher. We can see 3 products which all meet GRI GM13, they're all 1.5 millimeters thick, have a factor of 2.2 difference in how long they're going to last. Now, we were just looking at geomembranes 1.5 millimeters thick, and you may well ask, what is the effect of thickness? Well, when it comes to antioxidant depletion, you could argue theoretically it should be proportional to the square of the thickness. But when you do tests, it doesn't work out to be that simple. If we compare 1.5, 2, and 2.5 millimeters from the same manufacturer produced at approximately the same time, we find that the 2 millimeter has a 30% longer time to depletion than 1.5 millimeters, and 2.5 about 50% longer, but both substantially less than what you would theoretically predict based on d squared. If we look at time to nominal failure based on a drop to 50% of the stress crack resistance, we get about a 20% benefit for 2 millimeters and about 70% benefit for 2.5. Now, there may be additional benefits to the increased thickness, such as slower antioxidant depletion, such as a different stress regime due to thickness. Here we're just looking at time to nominal failure. But thickness itself is not enough either. Remember I said all other things being equal. They rarely are. So geomembrane thickness has a significant impact on the depletion of antioxidants. A thicker geomembrane, other things being equal, has a longer antioxidant depletion time and time to nominal failure. And you may warrant a thicker geomembrane when you need a longer service life. And some landfill regulations require, for example, a thicker geomembrane for one liner than another in order to get a better service life for that particular geomembrane. So the geomembrane itself, the polymer, is important, but it's only one of the factors. The elements are also very important. We've talked about UV, we've talked about temperature, and of course physical damage if you have an exposed geomembrane. The chemical composition of the fluid is important. I've already hinted that to you. I want to emphasize it a little more. Here are values of time to nominal failure at 30 degrees. This is based on Arrhenius plots based on temperatures or tests conducted at temperatures above 30 degrees. And they're all for simulated municipal solid waste leachate. The full leachate is L3. And in L1 and L2, we took out the various constituents of the leachate, so we could try and identify how different leachate constituents affect the geomembrane's performance. And if you look at this, you can see that L2, in terms of the time to antioxidant depletion, is the most generous. 21 years it takes, compared to 28 years for L1 and 24 years for L3. So L2 is aggressive in terms of antioxidant depletion. But if we look time to nominal failure, we get a very different story. Now L3 is the critical one, and L2 is the least critical at 83 years. And that's because different constituents in the leachate affect different stages in its life. So the constituents in L2 have a big effect on stage 1, but very little effect on stages 2 and 3. So the characteristics, the chemical composition of the leachate is important. For example, surfactants, soaps basically, in municipal solid waste leachate and some heap leach solutions do have a significant effect on OIT depletion. Salts, on the other hand, we saw in the case of brine, and it's also true for municipal solid waste leachate, don't much affect. In fact, they may hinder OIT depletion. But they have a significant effect on the latter stages of degradation. pH can have a very significant effect, but how it affects is very sensitive to the particular antioxidant packages. Some are better for high pH, some are better for low pH. And chlorine, as you find in treated water, can be particularly aggressive. So if we want to summarize what I've been saying, we can say that standard and HPOIT depletion rates will depend on the incubation media and temperature. The efficacy of HPOIT in protecting the geomembrane depends on the compatibility of that package with the incubation media, and it also depends on the mechanism of degradation in that fluid. And as a result, it's very difficult to predict how effective a geomembrane will be in contact with a given fluid from the initial values, even from oven aging in air at 85 degrees for 90 days. It really doesn't tell you very much about the long-term performance of that geomembrane in a given solution, other than air. So one cannot tell a priori which is better at predicting the geomembrane, standard OIT or HPOIT. There are cases where HPOIT can be beneficial. High values of HPOIT may sometimes improve performance, but when immersed, mostly they don't. And even then, that generalization has to be qualified. It does depend on the specific package and temperature. Also, if you looked at some of the comparisons, or you look at them more carefully that I just gave you, you'll see that a geomembrane that performs really well in one solution is not necessarily going to be your best performer in another solution. So, is higher HPOIT the answer to slowing antioxidant depletion and improving geomembrane performance? It depends. In some cases, yes, it does help. In some cases, it has absolutely no effect. Now we come to temperature. You will recall I talked about times to nominal failure at 85 in periods of months. I talked about times at 30 degrees in years. Temperature is that difference. And we can get quite a wide range of temperatures depending on the condition. If we are exposed to the sun in Canada, it could be anywhere between minus 40 and 70. If we have a benign waste that doesn't generate heat, after time it will tend towards your annual average temperature. But if you have a waste that generates heat, then that depends on the nature of that particular waste. For normal landfills, 30 to 40. For extra moisture in landfills, 40 to 60. Ash fills, 65 to 70. Some heap leach pads are at 70 to 80. Unusual landfills, Tim will talk about, can be over 85. And brine ponds, depending on the conditions and whether you're trying to control the temperature, could be 40 to 95 degrees. So let's see how that temperature affects the time to nominal failure. And we're going to look at geomembrane MYC, which is 1.5, in an aggressive municipal solid waste leachate. And we have at 60 degrees a 9-year time to nominal failure. We can be very confident of that because we actually ran this test for 9 years. The rest of the numbers are projections based on an Arrhenius plot for a range of different temperatures. And you can see as we go from 60 temperature to 30, we go from 9 to 60 years. So there's more than a 6-fold difference as we drop from 60 to 30 degrees. Temperature matters. Here's another geomembrane we tested, MYA. It's 2 millimeters thick. And at 60 degrees, we project 13 years. Again, we can be very confident. We ran this test for 17 years. You've got to have a lot of patience in this business. The rest are projections, but you can see a very significant effect. 13 years at 60 through to 430 years at 30 degrees Celsius. Now, what we've been talking about are immersed in solution. It's a nice test to do because it is relatively easy, even if you still have to have a lot of patience. You immerse it in a fluid and you periodically test it. What could be easier? But it's not what happens in the field. a much closer simulation of what happens in your field is achieved with a geosynthetic liner longevity simulator, where we can build the full liner system. Here we have a compacted clay. It could be a subgrade of sand with a GCL on top of it. Here we have a GCL as well. We have a geomembrane. We have a geotextile protection layer. We have a gravel drainage layer, and we have leachate flowing in the gravel. And we can heat these up anywhere we like, up to 95 degrees Celsius. Now what we can do is we can test the same geomembrane in two different configurations and get a correlation between aging in jars and aging in a more realistic situation. And if we do that, what we find for product MXA is that in a real liner system with a relatively typical geotextile protection layer, about 600